Welcome to the exercises for Chapter 5. This chapter is all about methods to simulate data while learning about statistics. I am a huge fan of simulating data to learn about statistical analyses for a multitude of reasons that I explain in detail in this chapter and in earlier chapters. Okay, and in videos and courses and in person, I talk about it a lot. Okay, so let's start with exercise 1. The purpose of this exercise is to generate small samples of data using specific population parameters for the mean and the variance, and then see qualitatively and also a bit quantitatively how these sample characteristics map onto the population parameters. So to start with, we create a small data set of 10 numbers. These are 10 random numbers drawn from a normal distribution or Gaussian distribution with a mean of 0 and a variance of 2. Now here's the thing. These are the population characteristics. These are the population data, mean of 0 and a variance of 2. But any individual sample randomly drawn from this distribution is not guaranteed to have exactly these same characteristics. They should be roughly close, but not exactly the same. And so that is the main point of the first part of this exercise. So compute and report the sample mean and the sample variance of 10 numbers randomly drawn from this population. So I'm going to switch to Python, show you the code for this part of the exercise. This is not the full exercise. There's more to it, but I'm going to switch to Python and then come back to the rest of this exercise in a moment. So you can see that I'm using the numpy.random module. Now I've already imported numpy earlier in this script, and I'm specifying that the population mean should be 0, the population standard deviation should be 2, and the sample size should be 10. Now here you just have to be a bit mindful that in the exercise in the text, I said that the population variance should be 2, but here in numpy.random.normal, we actually input the standard deviation, not the variance. So that was actually part of this exercise, was just to help remind you that there is a difference between the variance and the standard deviation, and in NumPy, we specify the standard deviation. Okay, so we can, naively expect that the standard deviation should be, the mean of this sample should be 0, and the variance computed through numpy.var should be 2. But it's not exactly that. And why is that a discrepancy? Because, we are just generating a small sample from a theoretical population. So the sample characteristics don't always map perfectly onto the population parameters. So we can try running this over and over and over again. You see, it should be generally close to, here it's some far away, so it should be generally close to 0 and 2. Sometimes it's closer and sometimes it's further away. Okay, here it was pretty close, at least for the variance. Now, I hope you have the intuition that the larger the sample size, the closer the match between the empirical sample characteristics and the population parameters. That is, I hope that feels intuitive. That is actually codified in something called the law of large numbers, which I'm going to explain later in the book. But for now, I'm just going to set this to be, let's say, 10,000. So now we are generating samples, exactly the same population characteristics, but just with a much larger sample size. The rest of this code obviously is identical. And here we see that the mean and variance are generally, as I run this more and more, they're closer to the population parameters, although they're still not exactly correct. Now for the next part of this exercise, which is an experiment. So we are going to set up a for loop where we vary the sample size between 10 and basically 10,000 in steps of 200. I went up to 10,010 because if I just wrote up to 10,000 in steps of 200, then we would actually end up below 10,000, which is also fine. There's nothing special about the number 10,000. Okay, so in each iteration of the for loop, we want to create a new random data set using exactly the same population, mean, and variance, but a different sample size. In other words, we are going to continually draw new random samples from this theoretical population with the same population parameters, just with different sample sizes. And then we can plot the results in a figure that looks something like this. Here we see sample sizes on the x-axis. Here is the empirical sample mean and the empirical sample variance for all these different iterations in this experiment for loop. So I'm going to talk more about how to interpret this and what conclusions we can draw from these two plots. But first I'll show you the code in Python. So this code is, I think, pretty straightforward. Here I'm taking the code from the previous cell where I generate the random numbers and then compute their means and variances, and I'm just making some small adjustments to put in to store these results, these characteristics, in vectors that I define here, initialize them here. And here is the vector of sample sizes. You can see I'm going from 10 to 10,000 in steps of 200. And then here I'm just plotting the results of the experiment as well as the expected values of the results. So I expect that the results for the mean will be 0, and I expect that the results for the variance will be 2. Now, I guess one thing I can mention here is that these values 0 and 2 are hard-coded. Here in the plotting code, they're also hard-coded here. So if you would like to explore different values, you can, if you like, you can create new variables here for the population mean and population variance, and then you'd be able to explore this code more flexibly. Okay, but anyway, that's fine for now. Let's run this code and see what we can see. Okay, so again, this dotted dashed black line here shows the expected value, and the gray squares are all the sample characteristic values for these different sample sizes. So a couple things we can notice here. One is that the empirical averages are sometimes below the expected value and sometimes above the expected value. This is an indicator. This suggests that the sample mean is not a biased indicator of the population mean. So it's not always fully accurate, but it's also not biased one way or the other. So it's not like these values are always above the population mean. That would indicate that there's some kind of systematic bias, which would be more problematic. Non-systematic biases are better. I mean, ideally, we don't want any biases or inaccuracies, but if we are going to have inaccuracies and biases, we want them to be non-systematic, which suggests that repeating the experiment over and over again will converge to the true population mean. And again, that's codified in the law of large numbers and the central limit theorem, and you will learn about these concepts later in the book. Another thing you can see from these plots is that when the sample size is very small, the deviations from the population, the expected theoretical population means, are larger. So these deviations are big. As the sample size gets bigger and bigger, the deviations get smaller. So we're getting closer and closer to the true values, but we still never really get right smack on it, right? There's always some variability, some error, even with really large samples. So that's important to understand about statistics, because even when we're doing everything right, even when you have a large sample size, you have everything in your experiment as controlled as possible, you're doing everything in the right way, there's still no guarantee that your empirical sample is going to be a perfect match to the true population characteristics. Everything I just said is true for the average and is also true for the variance. Welcome to exercise 2 of chapter 5. The goal of this exercise is to explore the empirical and the analytic or theoretical means and standard deviations of a uniform distribution. So this follows from the previous exercise where we explored this relationship in a normal distribution. Okay, so create a data set of 1,324 numbers, because, I don't know, that's a good number of numbers, uniformly distributed between -3 and +8. Then you want to compute the mean and the variance of that data set using the mean and variance functions in NumPy, and then compute the expected values of those characteristics using equations 5.7 and 5.8. I will scroll up and show you those equations in a moment. So that's going to give you four numbers. So you have the empirical mean and variance and the expected mean and variance. Now, we don't actually care about those four numbers per se. We care about how close they are to each other. So the concordance between those two sets of numbers. So you can compute the discrepancy in terms of the difference in the mean values between the empirical and the expected, and the difference squared of the variance values. And I will explain later why I say to square the discrepancy for variance, but keep the signed discrepancy for the mean. Okay, so yeah, you won't be surprised that these values are not exactly zero, but we just want to write some code and confirm that at least the empirical and analytic values are pretty close, qualitatively speaking. They're relatively close to each other. Okay, so there's more to this exercise than just what I explained, but I'm going to get back to the experiment in a moment. First, I want to show you the equations, and then I will switch to Python and we'll see how to implement them. So here are the two equations for the analytic or expected mean and variance of a uniform distribution, where A and B are the upper and lower bounds of that distribution. So where do these numbers come from and how do we derive them? I'm actually going to walk you through that later on in the book, in a later chapter. For now, I hope that the empirical average is intuitive, that we have the two boundaries and we just take their average. And that gives us the theoretical mean. And the variance looks weird. Why do we divide by 12? Why is it A minus B? And so on. I promise this will make sense. I'm going to show you how to derive this equation, but that comes later in the book. So for now, suffice it to say, this is the expected variance. This is the expected mean. So here we are in Python. Here I generate uniform distributed numbers with these boundaries and this sample size. Here is, this comment is not entirely accurate. It's not just the mean and the variance. It's the mean and the variance discrepancy between the empirical values, which you see here, and the theoretical or expected values, which you see here. So that's for the mean. Here is for the variance. This follows the formulas that I showed in the book a moment ago. And now here I'm squaring this discrepancy for the variance difference. Now, we expect these in theory to be zero. They should be zero. Are they going to be exactly zero? That remains to be seen. And here I'm also plotting a histogram. This is just because, yeah, it's good practice to show distributions of data or to visualize data whenever possible. In this case, this is also going to help us confirm that we have simulated these data in the correct way. So we see that these data are uniformly distributed between -3 and +8. Of course, this is not a perfect uniform distribution because we are sampling a finite number of values from this theoretical infinite population of uniform distributed numbers. So here we see the discrepancies are pretty small. We want these to be zero. So we can run this again a few times, and you see they're always pretty close to zero. Now, the mean discrepancy can be negative. The variance discrepancy can never be negative because that's some quantity squared. Now for the experiment. You see that I set up a lot of exercises in a similar fashion, where I first ask you to write a little bit of code to give you some qualitative grasp on the concepts that I want to illustrate. And then we take that code and embed it into some kind of a for loop to run an experiment. Okay, so take the code you just wrote where we generate a uniform distribution and compute the discrepancy between the empirical and analytic mean and the empirical and analytic variance in a for loop ranging over sample sizes from 10 to 10,000 in steps of 200. Okay, so that's really similar. Here I want to add something else. So basically you define the boundary values A and B to be randomly selected between integers between -3 and 10. So that means that every iteration is going to have numbers randomly sampled from a different uniform distribution. So the shape of the distribution is the same. It's always uniform, but the values the boundaries will range randomly somewhere between -3 and +10. And obviously, you have to set this up so that, A, the left boundary, is always smaller than B, which is the right boundary. Then you want to visualize your results similar to how we visualize the results for exercise 1, and then draw some conclusions. So here is an example of what your plot might look like. So now I'm going to switch to Python. I'll show you the code that runs this experiment, generates this visualization, and then I will have a few remarks about this first panel and also this second panel, which seems like we have a bias in our variance estimate because we only have positive discrepancies. So more on that in a moment. If you have completed exercise 1, the previous exercise, you will recognize a lot of this code. In fact, when I was writing the code for this exercise, I really just copied and pasted and changed as necessary. Okay, so here I create the random boundaries, and you can see that I'm sorting these random integers. So random integers between -3 and +10 inclusive. So here we write 11. We want two numbers to get boundaries, and then I sort them, and this just guarantees that A will always be less than B, which is what we need to generate this uniform distribution. So here is the mean and variance discrepancies, and then here I generate the plot just like in the previous exercise, except here the expected values are all zeros because I'm computing the difference between two quantities that we expect in theory, in principle, to be the same. Okay, so let's run this code here, and n is not defined. Okay, so that's a little typo, which I will fix, so you will never see this. This was lowercase n here, and I just need to change that to uppercase n. All right, so here we see the mean differences. This is really similar. The conclusions that we can draw here are really similar to those from the previous exercise. And the conclusions are that although the empirical sample characteristics get closer to the population parameter with increasing sample size, we always have divergences. It's never a perfect estimator, and that is important to understand about statistics. Okay, and then we see the variance differences. This is striking. What's striking is that most of the values seem really small, and a couple of values look really large. These look like outliers. There's something wrong going on in these samples. And we also never get negative values. Every value is closer or further away from 0, but it's always positive. So this may lead you to wonder whether we have a systematic positive bias in the estimate of variance in uniform distributions. The answer is no. This is not a systematic bias because we are squaring. So obviously, we're only going to get positive values here. You can repeat this experiment. I'll do that right now. Instead of squaring, just get rid of the squaring altogether. And then we're going to see that this systematic bias disappears. And now we have values discrepancies that are above and below 0. Now, why did I ask you to do this if there is no bias? The reason is partly just to help you improve your coding skills and partly to help you understand what it would mean for there to be a systematic bias. It would mean that the empirical estimates are always in one direction, or more likely to be in one direction. That's not what we see here. It seems to be the case when we square the data values, and yeah, this is just good for your general statistical thinking skills to be aware of these kinds of issues and to understand the impact of squaring on data. Here we are with exercise 3 of chapter 5. Here we will continue working with simulated data of different distributions, in this case a log normal distribution, and the relationship between the theoretical mean and variance and the empirical sample mean and variance. Okay, so let's see. We want to produce a log normal data set according to equation 5.11. I will show you that in a moment, using the parameters mu equals 2 and sigma equals 1.5. And then we want to compute the mean of that sample data set. Now, I don't say here exactly what the sample size should be, so you can pick the sample size. It should be more than one and less than 10 quadrillion, because that's just going to take a really long time to compute. So in fact, you can explore, try different sample sizes and see whether the average of your data set conforms to a value of 2 approximately. And well, I think what you will discover is that it's not even close to 2. The average of y is not going to be close to 2. And what is going on? Well, what's going on is that the parameter mu is actually transformed through a nonlinear function, the natural exponential function. Okay, so let me show you the formula down here. It's this. So this is how we create a log normal distribution. So y equals e to the x times sigma plus mu. Mu is the population mean, sigma is the population standard deviation, and x is a data set of random, normally distributed numbers. So you start by creating Gaussian distributed numbers, we call that x, and then you apply this series of transformations to get y. So here's the thing. The mean of y is not going to be exactly equal to mu. Mu is this number here, and that gets passed through this nonlinear function here. So therefore, we have to figure out what is the empirical average, or what is the theoretical average, and how do we get that to map on to the empirical average. Okay, so what I want you to do is take a moment to solve this equation for mu. That's going to tell us how to compute the expected average of this distribution, this log normal distribution. I'm going to scroll down in a moment and show you the answers, but if you want to pause the video, then now is the opportunity to do that. And if you need a hint, then I will now give you a hint. The hint is, if you ever have an equation that you're trying to solve for with a natural exponential e to the something, and you want to get rid of the e, or bring down the something, then you take the natural log of both sides of this equation. Because the natural log and the natural exponential are inverse functions of each other, so therefore the log of e to the something is just something. And then you have the natural log of y over here. Okay, so here I show how to do this. You can see I'm taking the natural log of both sides of this equation. The natural log and the e are inverses. They cancel out. So we just get mu on this side, and the rest is just a little bit of algebra. Okay, so there's an experiment to run, but first I want to show you how to implement the first part of this exercise in code. So here are the parameters that we specify. Here is, I call this normal, but in the equations in the book, I call this capital X, like this. So it is normally distributed numbers with a standard normal distribution with a sample size of 10,000. And here is where I create the log normal distribution by passing the this variable x, normally distributed numbers, through this series of transformations. We have this linear transformation and then a nonlinear transformation. And then here is the mean, and here is the transformed mean. So this is just the mean of this distribution. This is that empirical mean transformed according to the equations where we solved for mu by taking the exponential out of the natural logarithm. Okay, or the natural exponent. So here we see the average is 22 something, like it's very, very large compared to the number that I specified, which is 2. But when we apply this back transformation, or like inverting the function, then we get a value that is very close to 2. And this is what we expect. So now when I keep running this again, you will see, yeah, this is always somewhere around 2, sometimes a little bit below 2, sometimes a little bit above 2. And this value is generally going to be not 2, so it's somewhere around 23 or so. Now, the next part of this exercise is to take the code that we just wrote and embed this in a for loop where we vary mu, we vary the population mean parameter in 13 steps between 1 and 10. And we're just going to keep sigma fixed at 1.5. If you would like to run additional experiments varying sigma, of course, I encourage you to do that. But just in the interest of keeping this problem one-dimensional, we're going to fix sigma and vary mu. Okay, and then we want to basically plot mu as a function of the direct arithmetic average of our sample and also the normalization or the inverse calculation that I just showed you. Okay, and then what we expect is that there's some nonlinear relationship here, and a linear should be basically perfect, except for, some variability due to sampling and noise. So here is the parameter for the mu's. Looks like must, but it's mu's, the various mu's that we are simulating here. Okay, so here in a for loop over these values of mu's, I have each value of mu and a looping index. So here I generate again the normal distribution, pass it through an exponential. Now this is slightly different from the code I wrote previously, but that's because I just took this stuff and embedded it inside the exponential function over here. It's exactly identical to write it in these two ways. And then we take the mean of that distribution. Now, here in this commented line, I'm just showing you that you could put all of this code, all three of these lines of code, into one line of code. But, this is more confusing. This is more difficult to look at, especially if you are new to statistics and or new to Python. So what I often recommend is certainly to start out writing code in this way. Yes, it's longer. Yes, it takes up more space. Yes, it requires more variables to be created, but it also helps you think about and process and understand what is going on inside this simulation. Once you are comfortable with the code written out like this, then if you want, this is purely optional, it doesn't matter. If you want, you can condense this all into one line of code like this. It really doesn't matter. And don't ever let anyone tell you that this line of code is better than these three lines of code. Forget people who say things like that. Okay, anyway, so then I apply this back transformation here directly in the line of plotting here. Okay, and then we see, this is more or less the line of unity. Of course, if you would zoom in, you would see that this line is not exactly unity because the empirical average is not going to match the theoretical expected population parameter exactly, but it's quite close. Visually, it appears to be perfect. What I'm showing you in this line is just solving this arithmetically. So here we're kind of demonstrating this to ourselves geometrically by looking at this line and seeing that it's straight. And here we can also subtract. So again, these are the theoretical values. These are the expected values of mu. And this is what we compute from our samples with a sample size of 10,000. Now, these discrepancies in principle should be zero, but they are not zero because these are empirical samples. So again, this is a really important concept to understand in statistics, that even with a sample size of 10,000, you're never going to, well, I shouldn't say never, but you're not really ever going to get sample characteristics that perfectly match the population parameters, certainly not in simulated data, and therefore not in empirical data, in real data values and real experimental data. The goal of exercise 4 in chapter 5 is to continue exploring uniform distributions, in particular the relationship between, on the one hand, the mean and the standard deviation of the distribution, and on the other hand, the two boundaries, so the lower and upper boundaries of the distribution. Now, when you create a uniform distribution using Python functions, you don't actually specify the mean and standard deviation. Instead, you only specify the two boundaries. Now, you know from previous exercises and earlier in this book chapter that there are formulas for this. So the average, the expected average, is just the average of the two boundaries. And it should also be intuitive that the standard deviation is related to the boundaries as well. The further apart the boundaries are from each other, the larger the standard deviation, obviously. Okay, so in this exercise, we are going to start by defining or coming up with formulas for the expected average, so the population average of the uniform distribution as a function of sigma, the standard deviation, and the lower bound, and also as a function of sigma and the upper bound, b. And then here I have the formula for the standard deviation as a function of the average and a function of a, the lower bound, and as a function of the upper bound and the average. Now, I've already written for you the answers here, so you know the answers. What you have to do, your goal in the beginning, is to derive these equations. So figure out how to get from, in particular, these four expressions. So here is 1, this is 2, and here we have 3, and this is expression 4. So how can you derive these four expressions based on equations 5.7 and 5.8? And here I give a little hint. And it's not so difficult. It doesn't require calculus or any like really difficult math. It's just a little bit of algebra, and maybe you make some false starts. That's fine. You just try again. Take my hint here. There's two equations, and you can set them equal to each other, and then you can solve for mu. And two other equations, you solve for b and set them equal to each other, and then you can solve for sigma. So let me now scroll up. I will show you equations 5.7 and 5.8, from which you can derive these two equations. So here we have equations 5.7 and 5.8. These tell us the mean and variance, population mean and population variance, as a function of the two boundaries. And what you want is to get mean, the mu, this characteristic mu, in terms of A and sigma, and in terms of B and sigma. And you define sigma in terms of A and mu, and in terms of B and mu. And then you will derive the equations, or you will get to the equations in the exercise. And the point of doing this, we're going to implement this in Python. I'll show you the code in a moment. But the real purpose of doing this is just to sit down and work with these equations by hand to help you gain a more flexible understanding, a more better grounding for understanding and working with uniform distributed data. All right, so I hope you found deriving these equations fairly straightforward and also fun and maybe a little bit insightful. Now for the empirical confirmation. So in Python, create a data set of 1001 random numbers drawn from uniform distribution with boundaries A and B drawn from random integers between -3 and +10. So you can reuse some code that we used in previous exercise. Basically so that every time you rerun the code, the boundaries A and B are going to be slightly different. Okay, and then you want to compute, here I say compute the two definitions of mu and the empirical average of the data set using numpy.mean, and then the theoretical average of the distribution, which is the mean of the boundaries. So let me just go back and make sure it's clear. So we are working not with this, that comes later. So now we're just working with this. And by the two expressions for mu, I'm referring to this one. This is one expression, and this is the other expression. And for now, you can use an empirical sigma. So you can compute the empirical standard deviation from the sample distribution to get this value of sigma here. And that you need to do. You need to compute this empirically because we do not yet have a value for sigma. We're going to do that next. All right, so here you see I specify the sample size. Here I get the bounds. This code is the same as what I used in a previous exercise. I'm just getting random integers between -3 and +10 inclusive, and then sorting them just to make sure that the lower, or that variable A corresponds to the lower bound, variable B corresponds to the upper bound. Here I generate the random numbers, and here is where I compute mu using A and mu using B. So you can see it's A plus the square root of 3 times the standard deviation of Y. And then here I have B minus that same quantity. Okay, and then I'm just going to print them out. You can see that they're all approximately 3. We don't expect them to be exactly equal to 3 because these are empirical measurements of a random sample. So we can run this again multiple times, and it's always going to be different, right? Because we are creating new random boundaries here. So we don't expect these to be exactly the same numbers from one run to the next, but we do expect all of these numbers to be somewhere around this value here, the average of the bounds. This is the expected value. So then we do basically the same thing. We want to compute sigma from A, sigma from B, and then the empirical standard deviation of the data set. Again, these should all be roughly comparable to each other. So here you see the code here, and yeah, I'm computing sigma according to the formula, so based on the average of A and the boundary, and here is on the average of, I'm sorry, I said A, I meant Y, the data set, the average of the data set and the upper boundary B. And then here I'm just printing them out along with the empirical standard deviation, and these are all really, really, really close to each other. The final part of this exercise is actually quite useful. It's quite handy to know about. And this is if you want to create a sample data set with a uniform distribution where you don't specify the two boundaries. Maybe you don't care about the two boundaries. What you care about, what you want to specify are the mean and the standard deviation of the uniform distribution instead of worrying about the boundaries A and B. So you start by translating equation 5.9 into Python code, set the parameters. So these would be the population parameters, mean of 3.5 and expected standard deviation of 1.8 and a sample size of 100,000. Now notice what we are not doing here is specifying the upper and lower boundaries of the distribution. So what you need to do is figure out what are the values of A and B. What are the boundaries of this uniform distribution such that they will have an average of 3.5 and a standard deviation of 1.8. Okay, so let me scroll up. I will show you this equation, and then I will switch to Python code. So here is the equation that you want to implement in Python. So you start with uniform distributed numbers. So this is a standard uniform distribution with a lower bound of 0 and an upper bound of 1. Here I call that variable u. And then you take 2u minus 1 and then multiply that by the square root of 3 times sigma. And then you shift that distribution by the desired population mean, or mu. And then, yeah, it looks like a weird formula. Where does it come from? Why do you say 2u minus 1? I explain in this paragraph here how to interpret this distribution. Nonetheless, for now, I'm going to switch to Python and show you how this looks when it's implemented in code. So pretty straightforward. I think we generate uniform distributed numbers, and then, just scale those up by 2, subtract 1. This term here basically just re-centers the distribution so that it has an expected mean of 0 and boundaries of -1 to +1. And then we scale it by the standard deviation, the desired standard deviation, and shift it by the mean. And that gives us a data set where we expect the mean, so the population mean is 3.5, and we get pretty close to that. Population standard deviation is 1.8, and we are very close to that. Here we are with exercise 5 of chapter 5. This is a pretty short exercise. It just requires some thinking, which happens in your brain. It doesn't require any coding, which happens in your fingers, although I guess coding is really also in your brain. Anyway, the question is, what are the expected medium and the expected mode of a uniform distribution with boundaries A and B? There's no coding for this. The answers are in the online code, but I'm actually just going to tell you the answers right now. The expected median of a uniform distribution is exactly the same as the expected mean of a uniform distribution, which is simply the average of the two boundaries. So that is the expected median. It's the same as the expected mean. In fact, whenever you have a symmetric distribution, you expect that the mean and the median are going to be the same In a theoretical analytic distribution, they're likely to be exactly identical. In an empirical distribution, so an empirical data set, the mean and the median of a symmetric distribution are going to be pretty close, probably not exactly identical just because of sampling variability and so on. But that's for the median. Okay, the mode, this one is maybe a little bit weirder to think about. You might be wondering, what is the most common value of a uniform distribution? The answer is all values are equally likely to be the mode. And that's because a distribution, a data set, can have multiple modes. Now, that's not true for the mean. A data set has exactly one mean and exactly one median, but a data set can have multiple modes. Mode is the most common value in the data set, and there can be more than one mode. So in a pure analytic uniform distribution, every single number between A and B is the mode. In an empirical distribution, it is likely that there will be one mode, or maybe two or three modes, maybe a few modes, but it's likely just because of sampling variability that there will be a small number of modes, maybe one. But that number could be literally anywhere from the entire distribution. And it's really just due to sampling variability and chance if one number happens to be present more than any other number. So there you go. From this exercise and the previous several exercises, you know how to characterize uniform distributions in terms of their boundaries, in terms of their means, in terms of their standard deviations, medians, and modes. I found this exercise, exercise 6 of chapter 5, to be really fun to develop and implement. So I hope you also enjoy working your way through it. There is a particular type of distribution called a triangular distribution. It's called a triangular distribution because its histogram looks like a triangle. And that you see here, an example. It takes 3 parameters, I guess you could say 4 if you include the sample size as a 4th parameter. But otherwise, the distribution itself takes 3 parameters, which are called A, C, and B. Now, in my humble opinion, I think they should have swapped B and C, because then it goes in order. But I think they called this A and B to be consistent with the parameters for a uniform distribution. Anyway, here you see the parameters are 0.2 for A, so that's the lower bound. 0.9 is B, that's the upper bound, and C is the peak of the distribution, and that is 0.6. And here you see what this histogram looks like with 10,000 samples. Now, there is a function in NumPy to generate random numbers drawn from a triangular distribution, but don't use it, at least not yet. Instead, I want you to search the web for the formula that creates a random numbers from a triangular distribution, and then implement that formula in Python code. I think this is useful because looking things up online and translating mathematical formulas into code is a really important and useful skill for any data scientist or really anyone who does any kind of scientific or quantitative coding. Okay, so so find a formula for the triangular distribution, implement it in Python, and generate a histogram of 10,000 numbers. Once you have done that, then you can use the Python function. I'm not going to tell you the name of the function. I will also leave that as a little challenge for you, but it does come in NumPy, and I think it's not so hard to figure out the name of the function and the way to use that function, and then produce another histogram. It will look also something like this. Okay, so here by Google searching for triangular distribution, we can get to the Wikipedia page for the triangular distribution. You can see here, this is the key visualization of the distribution with labels A, B over here on the right, and C in the middle. And then if we scroll down a little bit, we can see how to generate, where is this? Generating triangular distributed random variates. Let me zoom in a little bit more. Okay, so here is the function that creates a data set X of random numbers drawn from a triangular distribution. So you can see that there's this formula based on U, where U is standard uniform distributed random numbers. So random numbers drawn uniform between 0 and 1. And then you just have to, there's this kind of weird thing where the distribution data points get sampled according to these different formulas depending on this value of f of c. And this value f is a parameter that's based on the 4 parameters that you have specified, a, b, and c. So you have to implement this little piece of code, piece of math in code, and then this expression here in code. It's a fun little challenge, but it's not so difficult. And now I will switch to Python and show you my solution. So here again, I have the reference for where I got the math from, where I implemented these functions. So I chose 0.2, 0.6, and 0.9 as I showed in the figure in the book. And here is f of c. Here I generate the uniform distributed random numbers. And here is where I implement the two sides of that equation, which Wikipedia called variable x, capital X. Here I'm calling it y for no particular reason. So then we say, so if u is less than f of c, then we apply this part of the formula. If u is greater than f of c, we apply this part of the formula. And then we can just run all this code, generates the histogram. Very nice. We can repeat it multiple times. You can see the parameters are always the same because those are coded, but the exact distribution will look slightly different. So it's pretty neat. I encourage you to take a few moments and play around with this, try different parameters, see, I don't know, what's going to happen if you set C to be larger than B. Interesting thing for you to discover on your own. Okay, and then the NumPy function is called numpy.random.triangular. Not so surprising that that's what it would be called. The inputs are not so confusing. You just have to be mindful of the order. So the order of the input parameters are A, C, B. Now, in my mind, that is very intuitive. That makes a lot of sense because it's this bound, the middle value, the peak, and the upper bound. But they're just typically called A, C, B instead of A, B, C. I don't know, whatever. Anyway, then here I create another distribution with these parameters. And of course, it qualitatively looks exactly the same. So now you know about triangular distributions and how to create them. Triangular distributions are used in financial simulations, in time series data simulations. I think I don't use them so much in this book, but it's an interesting distribution to know about. And of course, the skill of translating formulas that you find online into code is super duper important. So I hope you enjoyed working through that. One of the themes of this chapter, chapter 5, is that you can generate data with different kinds of distributions by picking and choosing and combining and transforming numbers from different kinds of distributions and different mathematical or statistical transformations. And that is the goal of this exercise 7. So the goal here is to create a data set of random integers that have a normal distribution. So normally, when you create random integers, for example, sampled from the randint function, the distribution is uniform. You get a uniform distribution. On the other hand, if you want a normal distribution, so you want data generated from a normal distribution, you use the randn function, but you don't get integers, you get floating point numbers. So what do you do if you want to get integers drawn from a normal distribution? To my knowledge, as of this recording, there is no single Python function that will return random integers drawn from a normal distribution. So that is what you are going to do. You have to figure out some algorithm, some transformation, or whatever to get a distribution of random integers from a normal distribution. And here I say, don't worry about the width of the distribution. You can make it as narrow or as wide as you need to. Instead, focus just on the shape of the distribution. So we don't care about the numerical values. We just want the shape to be Gaussian and all the numbers to be integers. Okay, so as not to spoil the mystery, I have nothing else to say here in the text, but now I will switch to Python and basically talk about the solution that I came up with. Now, here's the thing. We can create integers from non-integer data just by rounding the numbers. So here I'm creating a standard normal distribution, 100,000 numbers randomly drawn from a standard normal distribution, and then I just round them. Okay, but when we look at the histogram, we can see, yeah, I mean, this does technically, according to the letter of the law, this conforms to the instructions that I specified in the exercise text. But I do not find this to be a very satisfying answer because there's so few numbers. There's only 9 unique numbers in this distribution. So therefore, what I'm going to do is just scale up the distribution. So here I'm creating random normal numbers with a mean of 0, although the mean doesn't actually matter, and the standard deviation that's much higher. So a standard deviation of 15, which is a really wide distribution relative to a standard normal distribution. And then I round those numbers. Okay, so now we can look at the histogram and count the number of unique numbers. To me, this looks much better. There are over 100 unique numbers in this data set. They're all integers. There's no fractions in here, no decimals, all integers. But you can see it has a beautiful, perfectly normal distribution shape. Now, it looks like there's some missing points in here, but that's just the way that the bin size ended up working out because I used the Friedman-Diaconis rule, which is based on the standard deviation and so on. So if you want, you could change the number of bins to make this look a little bit better. Actually, maybe let's just do that. Let's just say 40 bins. How about that? Okay, so now you see it looks a little bit nicer. Looks like there's a big thing up here, a big spike up here, but that's in part related to the fact that it overlaps with 0 here. Cool. So I hope you enjoyed working through this exercise. You learned how to create integers with a normal distribution shape. Exercise 8 of Chapter 5 is going to preview 2 important concepts that you will learn about later in this book. One concept is the correlation coefficient. That's a way of measuring the linear relationship between 2 variables, like height and weight. So people who are taller tend to weigh more than people who are shorter, who tend to weigh less. That's an example of a kind of relationship we would quantify with a correlation coefficient. And the other concept in this exercise is permutation testing, which has to do with creating a random data set or creating random data out of the empirical data that you have measured. So both of those topics will be discussed in detail at length in later chapters of the book. The goal here is to provide a nice, gentle introduction to those concepts in the context of learning about simulating data. All right, so let's get down to business. Here, what I want you to do is create a data matrix, so a NumPy array that is 100 rows and 2 columns that would reflect 100 observations and 2 variables. So for example, we measure the height and weight. Those are the 2 variables or 2 data features from 100 different people, and we want to know if they are related to each other. So start by creating a 100 by 2 data matrix with or comprising normally distributed random numbers. And then you want to set the second column to be itself plus the first column. This is one of many methods to create or to simulate correlated data, and you will learn other methods in a later chapter in chapter 12. Okay, so I'll show you figure 15 in a moment. Then once you have created this data matrix, I want you to compute the correlation coefficient between the 2 columns. Here I just very briefly introduce you to correlation coefficients. They vary from -1 to +1, and you can use the function numpy.corrcoef to obtain the correlation coefficient. Now, if you are not already familiar with the correlation analysis, then don't worry. This will feel a little bit like magic. You're not really going to know what's going on, but that's totally fine because then you can look forward to chapter 12 when you will learn all about the correlation coefficient and associated analyses. Okay, so the correlation coefficient is going to be somewhere around R. It's typical variable we give to correlation coefficient, somewhere around zero 0.6. Okay, so that is the first part of this exercise. When you plot the data, it's going to produce a graph that looks like this. Here we see the first column of data, the second column of data. I call these variables X and Y. Each data point, each dot here is an observation, and the empirical correlation coefficient is 0.62 in this particular case. Okay, so next, what you want to do is simulate one iteration of permutation testing, which I'm calling here randomization. Okay, so make a copy of the data matrix, and then using random integers, rearrange the rows of the first column without changing the rows of the second column. So basically, you have all the data values here in column 1, all the data values here in column 2. Now, originally, all these data values are paired together. And then what you want to do is randomly rotate, randomly shuffle one column without changing the other column. And here's the interesting thing about this randomization. The data values have not changed. So all these sample characteristics, the mean, standard deviation, skew, whatever else, are all identical. We haven't changed any of the numbers. We haven't transformed the numbers or manipulated the numbers. All we've done is shuffle the order in which those numbers appear. But because we shuffle the order for one column and not for the other column, that changes the correlation coefficient. In fact, we are destroying the correlation coefficient, and that you can see in this plot here. So in this particular case, we ended up with a correlation coefficient of 0.07. And you can see the dots here are exactly the same as the dots here. They're just rearranged on the x-axis. So you see, these 2 points here are these 2 points here. The y-axis variable is the same, only the x-axis coordinate has been randomly reassigned. So here is the code. So 100 normally distributed random numbers in a matrix, and here I'm redefining the second column to be itself plus the first column. And here's how we can use the correlation coefficient. I'm calling this R real, by the way, because this is the original correlation coefficient in the original data. That's going to be, we can compare that with the shuffled correlation coefficient that I'll show you in a moment. Now, the correlation coefficient, or the corcoef function, actually outputs, let me do this, actually outputs a small matrix. So it's ones on the diagonal and the correlation between the two variables on the off diagonal. Now, these are ones indicating that variable 1, which is the first column of this matrix, correlates perfectly with itself. This 1 over here indicates that the second column in the matrix correlates perfectly with itself, and this is the correlation coefficient between the two variables. Now, you might wonder why there is this crazy format, why, because this number is identical to this number. I'm going to explain in detail why we get that matrix, how to interpret it, how to visualize it, how to work with it, how to get p-values from it, and so on. That is coming later in chapter 12. For now, suffice it to say, we just need either one of these two variables. So therefore, I have this index here. It's just going to give me this one number like that. Okay, so that is the first part of the exercise. We have created a two variable data set where the variables are correlated with each other at somewhere around 0.6 to 0.7. Okay, so now for the permutation testing. So I'm going to get a random number index. These are random indices by permuting n. So the numbers 0 through 99. Okay, here I'm making a copy of the original data so we don't change the original data. And now here, notice I'm only changing the first column. We could call this variable x. I'm not changing the second column. I'm only changing the first column. And then I'm computing the correlation coefficient again. And again, we're only saving one of those off-diagonal elements. Okay, and then we can run this code here. So we find that the real correlation without shuffling the data is 0.671, and the shuffled correlation is 0.095. Now, because this is random, every time I rerun this code, I'm actually going to get a different shuffled correlation coefficient. This obviously is the same because uh, it is random data, but it's randomly generated data in this cell. So when I rerun this cell, I'm not actually changing the original data. That's pretty interesting to see that the correlation coefficient is the same, the data are the same. I'm not changing the data. All I'm changing is this, the shuffling correlation over here. So you can keep rerunning this. You'll see it's always somewhere around 0, but sometimes just purely by chance, you end up getting a correlation coefficient that is, pretty, I mean, that's not a big correlation coefficient, but if you have a large sample size, this could actually be a statistically significant correlation coefficient, even though it's literally truly random mapping between variable 1 and variable 2. Okay, so that is pretty interesting. And here is the plotting code. This part is not so interesting in the sense that, I'm just making a scatter plot between the first column and the second column. And then I print the correlation coefficient inside the title, and that you see here. So again, you will learn a lot more about the correlation coefficient later on in the book. But it's pretty interesting to see that with a correlation coefficient close to 0.7, it's visually obvious that there is a relationship between these two variables. And with this correlation, it's much more modest. It's 0.15. Again, if the sample size is large enough, this actually could be a statistically significant correlation coefficient. But you really don't see, I mean, it's not obvious. It really doesn't look like there's a real correlation. In fact, this might even be driven by a couple of these outlier points here, at least, relatively extreme points over here. So much more to say about that later in the book, but I hope you enjoyed working through this exercise. Exercise 9 of chapter 5 is fairly straightforward conceptually. The main purpose of this exercise is to introduce you to using Python functions, in particular from the scipy.stats library, that will allow you to create random generated data from lots and lots of different types of distributions. Now, as I mentioned earlier in this chapter, there are kind of two families of approaches to creating random data sets from various distributions. One is to implement the math yourself, or apply some kind of transformation, linear or nonlinear transformations to randomly generated data from a normal distribution or uniform distribution. Plenty of examples of that. The second way to generate random data is to use some distribution function in the stats library, or sometimes NumPy, but the scipy.stats library has more options for distributions. And the general format of this code looks something like this. So you will say stats dot, where stats is this module in the scipy library. So stats dot, and then some name of a distribution, dot RVS, and this stands for random variates, or random variables, random numbers. And then some number of inputs. You're generally always going to input a size. Some distributions require some additional inputs. Other distributions have some default settings for inputs and so on, but they generally follow this kind of formula. Okay, so then to help you get started, I would like you to create a figure that looks something like this. So here I created data from a Laplace distribution, and here you see all the data values, and I have here a dashed line corresponding to the standard deviation of this distribution. So you see, it looks a little bit like a normal distribution, but there's more data clustered towards 0 and less data further away from 0 relative to what you would expect for a Gaussian distribution. And you see that as well in this histogram here. So I have a histogram of these data. And I've also color-coded the bars so that you can differentiate all of the data that are within one standard deviation on either side of the mean versus further away from one standard deviation on either side of the mean. And here I think it's very obvious that it looks a little bit Gaussian-ish. It looks kind of like a normal distribution, but it tapers down much faster than what you would expect for a normal distribution. So it's real difference in kurtosis compared to a standard Gaussian distribution. Yeah, so that figure was created using the Laplace distribution, which is the term Laplace here. So let me scroll up here. So it would be stats.laplace.rvs, and that is how you create the data for figure 5.16. And then once you have the code written and once you are comfortable using the code, then I'd recommend just exploring different kinds of distributions. And you can start with norm, norm for exponential norm, and a Gumbel distribution, a right Gumbel. There's two, you can have asymmetric Gumbel distributions. So this would be a right Gumbel distribution. And then I'm going to show you in the Python code where to find a list of all of the distributions that you can experiment with. As I mentioned at the beginning of this video, conceptually and statistically, this exercise is not so difficult, but if you are new to Python, in particular new to Matplotlib, then you might find just the visualization aspects of this coding challenge to be difficult, in particular color coding the bars in the bar plot. If that's something you're struggling with, then, don't stress about that. Just look at my code and copy that and learn from it. So you have that code and you know how to do that in the future. Okay, so you can see that here I'm importing the scipy.stats library as just stats. Pretty typical way to import this library. And now I have here 4 lines. And so you can just uncomment any one of these lines to see what the distribution is. Norm, this is actually not anything new for you, right? You've seen normal distributions with a location or mean of 3 and a scale or standard deviation of 1. Okay, so the Laplace one is uncommented because that's what creates the distribution that I showed in that figure in the book. So here I get the mean and the standard deviation, compute the histogram values. I'm not directly creating a histogram. I'm using NumPy to get the histogram values. And the reason why I do that is I want to find which of these bars has, the set of bars that are greater than the mean minus 1 standard deviation and below the mean plus 1 standard deviation. And then I use that variable here, close bars, close to the mean, to draw 2 different bar plots. So a bar plot of the histogram bins that are close to the mean, that's this one, and then the ones that are further away from the mean, that's going to be this one. So you can see these 2 lines of code are really similar. I'm just changing the color of them, and of course also changing the label. Okay, so I hope this helped. It's basically just drawing the bars separately depending on their distance to the mean. Okay, so then we get a plot that looks like this. Here is the URL for all of the distributions that come with the stats library. And then, basically for this exercise, just to make things easier for yourself, I encourage you just to stick to the continuous distributions. So here we are on that website. This is the scipy.org website, and it's just following the link that I pasted there. So here are all the different distributions that you can explore. You can see there are many of them. I gave you a few suggestions just to help you get started, but go nuts with this stuff. Kappa 4, what does a Kappa 4 distribution look like? Here is the crazy looking formula for a Kappa 4 distribution, but you can actually generate random numbers from this distribution just by, here I wanted to see a picture. Actually looks a little bit like an F distribution, although this has negative values as well. So pretty neat to see what this distribution looks like. Here are the parameters that you would specify. And so basically by just playing around with the code, you can gain more experience with different kinds of distributions, different characteristics of distributions, the impact of different parameters of distributions, and so on. I definitely encourage you, this is one of the most amazing parts of using code to learn applied math and statistics is you can just experiment and start gaining some real valuable intuition. This is the video for exercise 10 of chapter 5, but I want to open this video by showing you figure 9, which is a figure from earlier in this chapter. This is a figure where I introduced you to the idea of running experiments on simulated data to understand statistics and the behavior of statistical operations, particularly in the presence of noise and sampling variability. Okay, so just as a quick reminder, in this experiment, we were exploring whether the mean, the average of a sample, is related to the standard deviation of that sample. Now, in principle, the mean and the standard deviation of a normal distribution have nothing whatsoever to do with each other. You can have the mean for any standard deviation. The mean is going to be the same. But when we have finite samples, we have sampling variability. And that means that purely by chance, even, if you did your experiment in the right way, you did everything correctly, but it's just going to happen that by chance, your empirical sample mean is going to be different from the true population mean. And the larger the standard deviation, the larger the risk of having a big deviance between your sample empirical mean and the true population mean. So this is an important concept in practical statistics. Okay, but so you see that the expected average is 0 the whole way through. As I mentioned, the mean and the standard deviation are unrelated to each other for a normal distribution. And this brings us to exercise 10. So basically you want to repeat that experiment. In fact, I recommend starting with exactly the same code. So just find the code that corresponds to that figure in the code file for this chapter, copy that code, paste it into a new cell, and then repeat it, but use a log normal distribution instead of a normal distribution. Okay, so then we want to use 10,000, sample size of 10,000. Again, leave mu to be 0 and vary sigma in 40 steps between 0.01 and 10. Okay, and here I say you just have to be aware that the expected mean of a log normal distribution is not this value of mu, but instead it's a nonlinear function of mu and sigma. I explained that earlier in the chapter, and also there was an exercise entirely dedicated to this concept. So you will need to modify the code a little bit. Okay, you're going to get a figure that looks something like this. So a couple of striking things that you notice about this figure. One is that the mean and the standard deviation are no longer independent of each other. So this is the empirical mean and the mu parameter. They are the sigma parameter, which you vary from 0.01 to 10. These are no longer independent of each other. And part of the reason for that comes from the formula of the log normal distribution. But we can also think about this intuitively, because to create a log normal distribution, you take the natural exponential of normally distributed data. The natural exponential, so e to the something, is a strictly positive valued function. So we cannot have negative numbers, which means that as the variability of the normally distributed numbers increases, the log normal distribution can only be pulled to the right. It cannot be pulled to the left because we have a floor at 0, or, not literally 0, but some number very, very close to 0. So we can only shift the distribution to the right. Okay, so that is about this dashed line. But here, there's a real bias, right? So this is not a bias that we impose because we're doing, we're sort of squaring and then taking negative or something like that. This is a real bias, which really comes from the data. It comes from the simulation. And basically, we are not able to accurately estimate the empirical mean of this simulated data set for larger standard deviations. And it looks like it does a pretty good job up to around 4, 5, or 4.5, something like that. And then we really get this negative bias. Now, there's nothing special about a sigma parameter of 4.5 or 4.8 or whatever. That's just how this figure ended up working out based on the sample size and so on. So don't think that there's anything special about this divergence. The point is that the overlap between the expected and the empirical means is pretty close for relatively small standard deviations And as the sigma parameter gets larger and larger, we have this systematic bias to underestimate the mean. Okay, now I'm going to talk more about why that happens and give you some illustrations when I get to the code. For now, I want to switch to Python and just implement the code, show you the code that creates this figure here. Okay, so here is the code. It looks very similar to the code that produces figure 9 in this chapter, which is earlier. You could scroll up in this code file to get to that code. Okay, so let's see. Here we have our sigma parameters. They vary from 0.01 to 10. The mu parameter and the sample size are fixed at 10,000. And I have to say, might be a little bit ambiguous. This is not the mean and the standard deviation of the log normal distribution. This is the mean and standard deviation of the normal distribution, the normally distributed data, which I then push through the natural exponential function in order to get the log normal distribution. So the mean of the log normal distribution is not going to be 0, but we have to apply an inverse transformation to the formula. And again, I talked about that in the book and a couple of exercises ago. Okay, so here is the key for loop for this experiment. We're looping through the standard deviations. And here is the normal distribution. And here I shift and scale and then non-linearly transform this normally distributed set of numbers into the data that we are going to work with. Here is how I apply the inverse transformation to get the expected mean. And that's going to be that black dashed line that I showed you in the figure. And then I have this variable results, which is the empirical average of this data set. Okay, so again, if the universe were kind, then we would expect that these black squares to overlap with this dashed line nearly perfectly. Again, sampling variability and noise and so on. It doesn't need to be exactly identical, but we certainly don't like to see this systematic bias. Okay, so why is this happening? This is happening because the distribution is getting so variable, it's getting so far pushed off to the right that these numbers that we're basically missing numbers. Okay, let me actually just illustrate this to you. What I'm doing in this code cell is showing two histograms of the data. And let me start by just showing this. Okay, so this histogram's not of the data, but the log transform of the data for two specific values of sigma, a relatively small value and a relatively large value. So let me just go back up here. So I'm showing histograms of data using this parameter where there was a really close match, and this parameter for sigma where there was a strong mismatch. Okay, so the histograms show the log transform of the data, not the data itself. The vertical line here shows the log transform of the mean. Again, this is not the actual average of the data, it's the log of the average. So it looks like it's wrong, right? But that's because these data are all log transformed. So they're actually getting stretched out. So actually, in this plot, they are compressed. The data are compressed. The real data values are much more stretched out to the right. So these values are really, really big. They are way, 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 way larger than these values. So it looks artificially symmetric because we applied this nonlinear transformation. This is even more extreme. But look at these numerical values. This is 20, this gets out to like 25 or so. These are absolutely huge numbers over here. And so the numbers are so big that it pulls the mean all the way up. Now that you've seen this, I want to show it to you again without the log transform. So I'm just going to remove the log. Here, this is still going to be the mean. And then let's regenerate this plot here. So now you see what this looks like. So now this vertical line is much more sensible, right? So you see a lot of the data are clustered to the left, but there are data values here that are so extreme that it pulls the mean all the way up. This is now no longer correct. This is the true data values, not the natural log of the data values. And now look what happens here. There's so few values that are this large that they barely show up on this histogram. But when there are data values this large, they're very infrequent, they're very rare. But when they are there, they are so phantasmagorically ginormous. I don't know if those are real words, but they're so huge that they really, really strongly pull the mean up from the bulk of the distribution. Okay, so I hope that part makes sense. Now, given that, what is happening here, and the reason why we have this systematic underestimation is that these large values are so unlikely to occur in practice when sampling a finite amount of data that they just don't get sampled very often. They are underrepresented. They are theoretically in the distribution, so that the analytic mean incorporates those extremely rare events, but when we sample from our random number generator or when we sample from the world, those numbers are just so unlikely to be present. And so their impact, which should be there, they should be pulling up the mean from lower values, is just absent. So we get this systematic underestimation. Now you can find, I'm not going to do that. Oh, maybe I'll do this. Okay, so let's see. This starts diverging around 4.5 or so. If we generate a much, much larger sample, so now I'll do 100,000 data points instead of 10,000 data points. That means that we have much more opportunities for these really, really low frequency events to be sampled. So now you see, it looks like there's a pretty good convergence between the expected and the empirical means up to around 6, sigma of 6. Remember, previously it was around 4.5 or 5 or so. You can make this even bigger. Let's make this 1,000,000. That's a large number of data points. And now, okay, actually that wasn't that much better. So basically these data values are so incredibly unlikely that they even with 1,000,000 data points, they just don't get sampled that often because they're so big. So they should have an effect on the mean, but they don't because we're just missing them. They're just not being randomly sampled. I hope you enjoyed this exercise. I hope you found it puzzling and then enlightening. The main take-home message is that there are discrepancies between math that you see written down in equations, some people call chalkboard math, versus math as it actually gets implemented in practice on computers, in the real world, and in scientific experiments.